So today we are going to talk about Stern-Gerlach experiment. These two were different people who performed an experiment which led to something called as spin of an electron, which we all are very familiar with. But this is the first time that now we will be talking a little bit about the physics part. Till now we were talking mostly about mathematical aspects. Now we are shifting slowly towards the physics part. Okay. So what was this experiment about, and what were we talking? So this is the basic schematic diagram. There is a oval and silver atoms are heated and are sent through a magnetic field gradient. This magnetic field not homogeneous. So the first question that arises is that why silver atoms? Why in particular these atoms? So silver atom can be represented by this. There is krypton, and there is d orbital which contains 10 electrons, and there is this one. So how many atoms? How many electrons? So there are a total of 47 electrons. 46 do not contribute to any net angular momentum. So they do not produce any because they are spherically symmetric. This is an even number, so they all cancel out any angular momentum. There is one electron left, so this will contribute. So now all atoms have certain magnetic momentum, magnetic moment. And how it is defined? So mu is equals to charge of electron, Planck constant, and the mass. So magnetic moment of nucleus, and that will be mass of nucleus, and magnetic moment of an atom as a whole. Not, sorry, magnetic moment of an electron So magnetic moment is in a way talking about the angular momentum part, and this is what these people are interested in finding, that what will be the angular momentum. So since there is only one electron that we know will contribute to the angular momentum, now there is also this question that we are throwing out atoms. Atom has a nucleus also. So we need to cancel out this possibility that whatever angular momentum that will be detected is not from nucleus and is solely from the electron, because this will be very much little in the nucleus, because mass of nucleus is very high, so it is in the denominator, so mu n will be very very less, and mu of this electron will be very very high. So that's why this one electron's magnetic moment, or in a way angular momentum of some sort, will contribute. So what they were expecting was this. Screen where they want to see these electrons, and what they were expecting was a straight line. Why straight line? So they were expecting that this will be all values of mu. This is since this is z dash. So all the magnetic moments will be available from minus mu z to plus mu z. We were expecting there will be a straight line. This was expected, but what they were able to see was instead of a continuous line, there were two bright spots separated by some distance. So this led to something called as space quantization. Space is quantized, nothing exists in between, or this led to a term called spin angular momentum, which is famously just called the spin of an electron. So orbital angular momentum is something like this, but spin, well, one should not try to imagine its physical attributes, that it's rotating on its own axis. That is also a very wrong picture. I'll tell you someday why. But this is something that happened, and we can talk about one more thing, that what is the force experienced by these electrons under this magnetic field. So we have talked about the magnetic moment. So basically this magnetic moment interacts with this magnetic field, and the resultant energy, interaction energy, is given by this. Dot product B magnetic field. And how do I obtain force is nothing but negative gradient of energy, and since in our case this is only happening in z direction, so we can just write this. Now we have a better reason that why there should be a magnetic field gradient, because if there is no gradient there will be no force, a net force acting on these electrons, and we will not have these results. So this is the force that is acting on these electrons. So now since the experiment was done and the spin part was experimentally verified, so we know that this is what the result was. Conventionally, that is the reason that we call spin up or down, because there is two spins, one is up, one is down. Right? So now to go further in analysis, the sequential Stern-Gerlach experiment was done. There were sequences of other measurements. So you have it all, and you throw out the beam, and you Stern-Gerlach setup, which is oriented in the z direction, just as we did before, and you have two beams. We call it SZ plus and SZ minus. But what you do is you block this one. Just block this one. So this dot is not going to be visible, only one. And you extend this further and again make a measurement with the same Stern-Gerlach experiment in z direction, and what you get is purely z plus 1. Since we have blocked this one, in this filter this is going to block, so in the next filter this beam is not appearing again. Fine. Now again there is our two beams, Stern-Gerlach experiment, z direction, plus beam, blocking the minus one, and this time I'm going to give Stern-Gerlach experiment x direction. So this time I have two beams, x plus and minus. Now comes the interesting one, the third one. Now we'll be adding a third one. we are shooting silver atoms, Z-oriented SZ experiment, blocking the down beam SZ minus beam, only supplying with SZ plus. Again, orientation to the X direction, magnetic field is in the X direction, and what we are blocking is the minus SX minus beams, and only supplying with SX plus beams. Now again we are going to supply with this orientation of the Gerlach experiment. So, well, in this series of experiments we have already blocked this part, SZ minus beams. So one can expect that I should not again have this beam SZ beams. But in the experiment, both were observed. And this was a very shocking experiment result, that even though previously we blocked SZ minus beams, SZ minus beams, how come SZ minus states are appearing again? So this was the most fundamental result of the quantum mechanics. Why it was different from the classical mechanics, that measurement of simultaneous measurement of this SZ and SX is not possible. This experiment destroys all of the information from the previous experiment. It's just a new game. Once you have done the spin X part, doesn't matter what we have done previously, you start again. So it seems that SX plus beam states contains this two states, and similarly SZ contains SX plus, and of course so on. But remember that in classical mechanics there is no such problem. So in classical mechanics, there is no issue with the angular momentum. If you know omega z, you can specify omega z, specify z. If you know omega y, specify ly. There is no issue that I can only measure Lz or Ly with certain arbitrary certainty. If I know omega z, I know Lz, so on. But there is issue here. There is a certain different kind of angular momentum which does not allow me to do such kind of thing as similar to classical mechanics. So this was one of the most important results of the sequential Stern-Gerlach experiment. So what we have understood in this sequential Stern-Gerlach experiment can be related with any of the classical phenomena or something that is easily visible or easily understandable. So there is one analogy that we can relate it with the polarization of light. So consider monochromatic light. Is moving in z direction and is polarized in certain direction, let's say x or y. So what do we mean by polarization? We know that it is generally written as the oscillating electric field component. So how can we write this? Electric field component. Suppose it was polarized in the y direction, then we can write y polarized. So we can do one experiment. It's easily done. So suppose there is an unpolarized light. It's not polarized in any particular direction. So light is coming out from all the directions. The electric field component is oscillating in all directions, and it is then subjected or passed through a filter which is polarized in some x direction, and after coming out of this, light will be polarized only in this direction, and then this light is again subjected to the filter y direction, and it was observed that there is no light coming out of this. No light coming out of this. But again, if we do the same experiment, a very slight amount of change and I have a rotated X-prime filter, say about 45 degrees. And then again this light is passed through a filter of y prime. Light is observed. So previously unpolarized light is subjected to this filter, and then again passed through this X prime and the y prime filter. There is no light. But between these filters, if I put another filter which is rotated by 45 degrees with respect to x, then the light was observed. So it seems that putting a filter in between like this destroys all the previous information, which is very, very similar to what we have seen in the Stern-Gerlach experiment. So then, in some sense, we can relate the polarization of light with the Stern-Gerlach experiment. So we can make some analogy with Stern-Gerlach experiment, and first setup that we had, so So the spin Z plus or minus atoms that we obtain in the Stern-Gerlach experiment can be compared with the XY polarized light, something like this. There was no filter in between and you observed no light. Similarly, in the Stern-Gerlach experiment, we brought the minus light. We were not able to obtain the same light again after we put the same filter. And so what is X prime, Y prime? They are basically, this is X, Y. X prime, Y prime is just 45 degree. X is rotated by 45 degrees. So this is what I can relate with Sx plus or minus atoms in the Stern-Gerlach experiment. And electric field component from the there is a line here. So this is nothing but so X prime contains both X and Y, which in our case is what spin Z plus or minus atoms. So X prime filter has both X and Y. So X prime is nothing but linear combination of the X and Y filters. And similarly, we can do this for Y prime as well. Negative factor. Rest of the things are same. Just there is a negative, rest of the things are same. So for X prime and Y prime filter, we can write them as nothing but linear combinations of X and Y. So Sz plus or minus states can be written as linear combination of Sx plus or minus states. Reverse. Sx plus or minus atoms can be written as linear combinations as a plus minus atoms. So all of this suggests that we can write the spin states in some kind of vector. But it will mostly not be in real space. So for light, we are writing them as linear combination in real space. These are real space coordinates and vectors in real space. But it is possible that we will not be able to write the spin vector states not in the real space, but it will be some different dedicated spin states vector space. So a reasonable way to write spin x states this is the bracket notation of Dirac. So Sx plus state can be written as the linear combination of spin z eigenstates and minus with the minus sign. So what about spin y states? So we can write one more linear combination where instead of plain polarized light we use what can I say about electric field here? And we add one pi by 2 factor. Cos, there is sine. So if we plot this and try to see from front, we will see there is a light path traced in circular fashion. Or we can write this as a finance form like this, then you can notice that I by square root of 2 factor. So how can I similar fashion? Right. In Y states the linear combination of Sz Z minus, but notice this vector, there is a complex vector. So we have defined all the Sx, Sy states as linear combinations. So this is a more intuitive approach of defining these states. We'll need a 2D vector space to describe this spin state. must be a complex vector space because we have introduced the complex number here. This much we can reduce by combining it or trying to make an analogy with the classical experiment of the spin light polarization.